you. Good morning, everyone. Well, good noon. It's not even the afternoon or morning. Today, inshallah, we keep going, carrying on chapter 5 on the MOSFET. So, basically, what we did last time, we finished with this example, right? Good. So, today, we add a little bit of complexity. It's not so complicated. A little bit complexity to the model of the MOSFET. And as I said before, we are mainly talking about the NMOS and PMOS. We'll talk about it at the end also. But it's easy to get the PMOS. We know how to do that, how to do the trick. So, here today we start with an important parameter we did not talk about it before, which is the finite output resistance in saturation. Before, if you remember last class, we said that the output resistance, what's the output resistance? It's this resistance. Because this is the output, this is the input, right? This is the MOSFET model, the NMOS. Huh? Remember? Long time no see. Okay, so this is the NMOS. Remember that? Very quick description. We said it has 3 terminals, gate, drain, and source. This is the input voltage, and here is the output current. This voltage controls this current through this current source that we call voltage controlled current source. Bingo. We have the equation, which is the equation of the current I drain, ID, in the saturation. Yes or no? Because we will use MOSFET as an amplifier, and of course we need a model for that, in the saturation. So this is not in the triode. You understand? Good. Excellent. And we said that there is a huge resistance here between the drain and the source. Why? Because the voltage here, VDS, does not control the current. So delta VDS divided by delta ID is going to be 0, because not dependent on VDS. And we said that resistance is so huge, we call it output because it's at output, it's so huge that we can basically ignore it completely. And that's why it's deleted. Excellent, excellent. So this is a quick refresh after the turmoil of the midterms. Alright, today we are going to contradict ourselves a little bit. And we say that that resistance does exist actually. It's not completely out of the picture. And basically, what we mean by that, that basically if there is resistance, that means indeed VDS does control IDS. But how? We did not talk about it last time, and today, inshallah, we will talk about it. Okay? So, okay, let's see. Okay, that's not really a big deal. I don't want to read this. We'll keep it later on. Okay? So, alright. We'll explain these in the following slides, especially here. So basically we said that the pinch off started when the voltage, we said that the voltage over the channel in the saturation, or when VDS actually is above the overdrive, that voltage VDS actually modified the shape of the channel, which was rectangular, this way, initially, when VDS was very small. It modified it to this triangular shape, and that basically makes, basically why? Because now the voltage over the channel is not same everywhere, actually, okay? And we said that the voltage of the channel here is actually the overdrive voltage. Here, actually, close to the drain is overdrive minus VDS. And basically, because VDS increase until it reach overdrive, once it reach overdrive, the overdrive minus VDS becomes what? 0. And in that case, the voltage here is 0, multiplying the voltage by the capacitance to get the charge is going to be equal to 0. And that's what we call pinch off. Okay? That's what we call pinch off. I repeat. Good. So we said that because of VDS is increasing, we said that the voltage of the charge here, of this channel, of the charge here in the channel, is actually V over drive. That's the voltage. The voltage over any point here, over the channel, is not going to be the V over drive, because now VDS is influencing that voltage, and basically the voltage on any point is going to be V over drive minus the contribution of this voltage. So the maximum contribution of this voltage is going to be where? At the drain. So here, when at the start of the pinch off, okay, at the start of the pinch off, actually the pinch off started here, exactly at the drain, okay. So we said that here the voltage basically here is going to be overdrive minus what? Minus VDS, and VDS is in this case V overdrive. That's where the pinch off start. Is actually the limit or the border between the triode and the saturation. Okay, got it? Good. So in this case, this, which is the effective voltage here on the channel here, so it's going to be what? It's going to be 0. And that's basically the definition of the pinch off. Now there is no charge for the channel in here. Okay, that's what we said before. We are just keep going. As we keep increasing VDS, now we are going inside the saturation even further. Yes or no? We increase the voltage in here. Now the voltage here becomes what? Negative. And negative, 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 and the 0 will be here. So basically the channel pinch off point will move forward. Back to where? To the source. Why? Because this voltage is kicking this pinch off point to the left. Yes or no? So typically what we say that the channel length now is gonna be reduced. Yes or no? The channel length will reduce. Because what's the channel? The channel was the whole L here. Was the physical length at the beginning. When we start the pinch off, at the pinch off itself, L is the same as the physical length. What's the physical length? It's this one. You remember? See? Oops. See, transistor in one line. Which is good. So this is what we call, so this is M plus, and plus, if you remember, the physical thing, this is the insulator. The channel is where? The channel is here. And we said initially this is L. Yes or no? Remember? The channel length. Even when VDS was small, L was the same as the physical length. Now, as we increase VDS above the overdrive, now the channel is actually shrinking. Very good. So basically now, L, the new L is L minus delta L. And delta L is actually this distance where my channel has left basically the drain. Got it? Got it? Good. Any question? Please ask. Alright, good. So now, we basically, remember here, we had here, on the bottom here, or around here, basically here, where I will use green here. So remember that we had here, all this is what? This area is actually depletion region, yes or no? Depletion region. Now the area here also is going to be depletion region, yes or no? So, you see what I'm saying here? So this is also depletion region. Because the channel, when he moves out, leaves that space empty of charge. That's basically what? A depletion. It's depleted of free moving carriers. Yes or no? Good? Good? Yes or no? Nice. Are you with us? Okay. Good. Alright, so sounds good. So we observe first of all that the channel has decreased. And then second of all, hey guys, the current, first of all, the current is going from the drain to the source, yes or no? But the electrons effectively, they are going where? From the source to the drain. So basically the electrons will come here through the channel, and then come here at the tip of the pinch off, they be shooted. It's like, gunshot. Shooted means at a very high speed. At the maximum speed they can reach, basically. So the voltage in here accelerates them until they reach maximum speed, and right there and then they go to the drain. They go to the drain. But at very high speed, at saturated speed. They will not go beyond that. That's it. You understand? They will not go beyond that speed from the channel to the drain. And I'll call it also saturation speed. It's not our topic, but that's fine. Alright, that's basically the physical description of what's going on in this saturation. Not only saturation, but in the region when VDS is actually go beyond the overdrive. See? So, in the worst case, for example, it can go here, the channel. See? It's even smaller than the original channel. So, what does it mean really? What does it mean? It means that VDS has controlled the length of the channel. Yes or no? So we say that the channel is modulated, it's controlled by. Yes or no? Controlled by what? by the voltage VDS. So this regime we call it the channel modulation, channel length modulation, because channel length basically is L. Now it's being modulated, being controlled by VDS. We will see next how to see this influence. Okay. Good. All right. Sounds good. Now we can. So basically the length has changed. Back to the equation in here. Remember this equation? This is the original equation. Okay. When we are where? Which equation is? When we are in the
VDS critical.
Saturation.
That's it. It's saturation. That's the ratio. That's it. Saturation. As soon as we start saturation, now this is our current. But then, hey guys, when VDS continue increasing, L we said decrease. Yes or no? Is there L here in this equation?
No.
Whoa! What's this?
Where is it?
Is it L? It's L. Ah. So the length has changed. So this current will do what? Will change. So VDS changed L, L changed ID. So now VDS changed ID. And in this case, we come to the conclusion that we have resistance. Yes or no? So through the channel modulation, VDS now controls ID. You see? Did you get that? Did you have it? So you see, that's the physical interpretation. So VDS change L, and L change ID. So VDS change ID. And that's basically Ohm's law. Yes or no? If the voltage control I, that means there's resistance. Yes or no? Make sense? Clear? Crystal clear. Alright, good. So we got it then. So in this case, we can put now resistance. We'll talk about how to get the resistance next. Alas? Good. So now, basically, what we have, when VDS now becomes so big, blah, blah. So what we have this term, we have this first term, which is the first term that we have when VDS was not controlling L. And then we add just a little bit of contribution of VDS through a parameter lambda. Okay? We said now, lambda is basically the relationship that relates, or the parameter that relates VDS to ID. It's just a constant. We'll see how to get lambda. So by adding this there in this equation, now we make the connection basically between the drain VDS and the current ID. Okay. Now ID is not only this current, but it's also this current, and that part is this part. Is this multiplied by the common factor? Did you get that? You understand? Mahmoud? Good. Got it? Alright, that's good. So, we need to know this now. We need to know how much R0 or R0. Usually it's called R0. Good, so let's keep going. Alright, sounds good. So, to calculate R0, as we said last before, is basically the inverse of the variation of ID with VD. Yes or no? So this is the definition. At what? At a constant VGS. We have to keep VGS constant because we don't want to, jump between the graphs. We have to be in the same graph. The graph of ID VDS, okay? Should not jump between graphs. And that was solved in the last example. If you remember when VGS changed, so the saturation current also changed. So we keep that constant. So great. So we count this. We take basically this formula, the formula that we just adopted just now, and then we play with it to get basically R0, the relationship between lambda and R0. Okay? Because lambda is just a constant, we don't know, and R0 we don't know. So we want to relate the two and try to make sense of what we are analyzing. That's it. So we take that current ID and we derive it with respect to VDS, keeping VGS constant. Good. Excellent. So that's basically that equation. Deriving, we are not bad in math, right? Well, good. So we take this. Of course, here now when we derive, we are not going, so basically the variation of lambda, we said that VDS will change, lambda change, yes or no? We take that variation and put it where? From L in lambda. Okay? Do you understand? So we said, okay, I want to keep L the same, But I want to introduce the parameter lambda where I have this relationship between VDS and ID. That's why. Now, L now in this case is constant. So these, they stay out. And what's the remaining thing? Is the derivation of this, which is nothing but lambda. Yes or no? That's it. Got it? Mahmoud? Good. So we have this. All what we need to do is just inverse it. That's it. We got this. Now this is what? This is R0. This is R0. Okay. Now what's neat about it? So, you know, as an engineers, we like to put things into nice presentation, you know, to make sense about the parameters that we are using. Alright, good. So in this case, so if we take this into things, so we have 1 over. Remember again, this value is actually ID without the channel modulation. Yes or no? That's the original one. Again, I'm using the green because I squared it, circled it in the previous one. Remember that? Which is this equation in green. This means without considering the channel modulation. The initial one. Okay, great. So this is ID. Very good. So lambda. So then I can write the whole thing as 1 over lambda ID. Yes or no? Great. Remember, this is R0. Make no mistake. Excellent. So the resistance here and ID here. So that means 1 over lambda is actually what? Is a voltage. صح ولا لا؟ لأنه resistance is a voltage over current. That's it. So we call that voltage VA. Means early voltage. This is the VA. I will have to change this guy. It's actually a big one. VA is called early voltage, named after the scientist who discovered the early effect, which is this channel modulation. Another name of that. Okay? Okay, this has been observed in many devices. The MOSFET became one of them. So very good, excellent. VA is constant actually. It's also a technology parameter. And ID now is the one that changes, yes or no? So it depends which ID you are. Not will change. But once ID is confirmed, the saturation current is confirmed, then R0 automatically will be calculated. Easy. Excellent. So if I give you VA, you can get lambda, yes or no? Because they are reverse to each other, yes or no? Yes. The inverse of each other. That's it. So this is number 1 gone. And once you get lambda of VA, then R0 will be done D. That's it. So now we have the last equation for the saturation, which is when VDS is way bigger than the overdrive. Yes or no? Got it? As actually, if you remember, just to take you back, I like history, you know. History is nice. So if you go back, where is that? That equation, you can see it in the original PowerPoint slides.
Which was it?
Yeah, long ago, you see. Midterms and exams and blah, blah. Okay, where's that? Hold on a second. This one. I see. But it was hidden here, yeah? Yes or no? I told you it was going to be hidden. See? Now we are covering it. See? Now we are covering it. That's the part that was hidden from you initially. It's too much, huh? Enjoy. That's what engineers do. Anyways, it's not really difficult. Once you understand what's going on, it'll be easy to do everything you want. It'll become fun stuff. Okay, good. So now let's keep going. So now we establish basically the full model. We establish the output resistance. What's the output resistance? It's nothing but R0. Remember that? And that's the R0 where it shows. So the real transistor, the MOSFET, is actually not flat. It's actually a little bit bended with the slope, because I have IDVD, the slope will be 1 over R0. And R0, I have the equation for R0. R0 is equal to what? R0 is equal to VA, which is a constant technology parameter over ID. And that ID, which one is actually ID? This one. The original ID. The pinch of ID. You understand? That's the idea here. So that you make no mistake. You understand? Because that's what I mentioned in the when we talked. That's what we mentioned where? Here. It's written here. This ID does not take into account the channel length modulation. That means just at the pitch off. Yes, that's the ID that you need to use. As soon as you start that, grab that ID, put it in memory, and enjoy. Alas, clear? Excellent. So make no mistakes, huh? No, good. All right. So what is that? Good question. It's a device parameter with the unit of 1/volt. صح ولا لا? Makes sense. The value of which depends on manufacturer design and manufacturing process. So it depends how the device was fabricated. If you want to go deep, there is a rule for that. Okay. But it is a technology parameter. It's from the foundry. When you buy a MOSFET in the data sheet, you will find lambda. Of course, why? Because lambda has also the VA. And now we come back to the graph again. So this is now the real MOSFET, or the closest to the real. So basically, if you take lines here, they all intersect a single point. And that's what Mr. Early found. That when he tried to make lines all together, he found them intersecting the line here of BDS at the same point. And then he started to ask himself why. And then he found that the early effect. And basically, if you think about it, the slope, that's what we are looking for. So the slope is nothing but what? 1/R, yes or no? So yes or no? So the slope is actually 1/R0, okay? But R0 is equal to what exactly? So it's actually, this slope is nothing but this divided by this, yes or no? This is what? This is almost like this, you see? And this is almost like this, and this is almost like this. That's why I need to use this voltage and call it, this is my current, high D. Oh, hold on a second. Oh, easy. Slope, oh yeah, that's right. Yes, ID, that's right. Divided by this distance, which is what? VA. He named it VA. My voltage, I found it. Early, found it, that's it. Now his name is ringing all over the world. Excellent, so now R0 is nothing but VA/I. That's it, you got it? As simple as that. But it is approximation, you see. It's not exact value, you have to consider. It's a little bit up than the intersection here. Little bit, tiny. Okay? That's why we use this value here. And then now, bingo, you see this divided by this, that's it. ID divided by VA, R0 is going to be VA/I. That's it. That's exactly the same equation that we found here. VA/I. Did you get that? Did you get that? VA/I. That's it. He found it graphically and maybe some theory. Graphical way. Even graphical way, you can get that. Say, for example, you do tracing, characteristic of MOSFET, you do it. If the manufacturer doesn't give it to you, you know how to get it. It could be a potential question for a quiz or a final. Did you get that? You better take notes. Did you get that? It's really important. See, now from a graph you can get these constants actually. Very important. يا ماحي so good. You don't need to take note. أنت اسمك حمادي يا ماحي متشابهين إلى حد ما. Sorry about that. خلاص, you don't take notes. You're fine. Remember this. I can ask you how to get me VA. From the graph. Of course. See? Because this is important. It's not written. It's a note. Okay? Alright. So please take notes. Okay. So from the graph, we can get these technology parameter, VA, early voltage. And from VA, you can get lambda, then you can put the equation in German. And R0, blah, blah, all these things. Excellent. Okay? Alright. That's it. So everything's been said, it's now drawn there. So nothing really. Don't cut on the video, by the way. Who's done with this? Fine? Everything's clear?
Yeah.
It's not clear, I wait, huh? I can move? Let's move on. Okay, great. Alright, back to the PMOS. So what we said in NMOS is just a symmetry, we get PMOS. صح ولا لا? Replacing N by P, P by N, and reversing the currents and voltages and everything will be a done deal. So basically this is what we did last time. And remember for NMOS, the body arrow here was going in towards the gate. Right? Now the current, as we said, is going from the source to the drain, not drain to the source. This is PMOS, remember? We are talking about PMOS. Technically we have said this. We are not just repeating ourselves. And the equation typically the same. Here is basically the equations for the PMOS in terms of the triode and the saturation. And basically they are exactly the opposite to the NMOS. Okay, I'll let you revise this. It's basically right away. Now VTS instead of saying VTS, now in PMOS we use VSD. That's it. VGS, VSG. And VTP should be taken in absolute value so that minus minus not becomes plus and we blow the equation away. That's it. So pretty much the same to some extent, of course. Of course, when PSG is less than VTP, so we don't have a channel. That's it. That's it. Just take the equations and flip everything and replace N by P, you are in PMOS. That's it. It's like a mirror, exactly like a mirror. You know the other side. Alas, move on. Alright, good. So, now we'll talk about the DC and we'll try to solve some problems. So, now we need to talk. So far, really, typically we are talking about using the MOSFET in DC. DC direct current. There's no changing. We just keep changing the battery voltage and that's it. We move on. It's not like a signal that's changing over time. We are not doing that. Alright, and so far also, at some point we neglected the channel length modulation. When we neglect that, that means we neglected R0 or R0. And typically, numerically, R0 is very high resistance. Make no mistake. It's very high. But now we can know how high it is. That's all. Okay? Alright, and of course, we will deal when we analyze the DC circuit, always like we did last time. We'll talk mainly about the overdrive as a parameter that it can help us to analyze the circuit, yes or no, when there is a channel or it's not, with triode, with saturation, things like that. We always keep talking about the overdrive. And here just I've seen something here we did not mention. When we neglect R0, means R0 is so high, so lambda will be what? Will be 0. Because they are inverse. That's it. Alright, who brought the textbook?
Said.
So only one textbook for the whole class?
We share it.
Oh, we agreed. I like that. So it was planned. Huh? Okay, let's go to this page. Huh? Very good. I like that. No, not bad idea. Yeah. Okay, page 383. You have soft copy of the book? So page 383. So basically, this is what we have. We have this circuit. Huh? Yeah. Yeah, what?
The question.
Good for you. Good for you. So you can follow. Everyone who was follow class, not bad. Yeah. But I find it difficult to share the book with the whole class. It's a nice idea. Good luck. Alright, so this is the circuit we have. Huh? We have, this is NMOS or PMOS?
Yeah.
What's that? NMOS or PMOS?
NMOS.
Why is that?
Because it goes from the drain to source.
To the source. The current is to the source, not from the source.
Yes.
To the source for NMOS, from the source, PMOS. Very easy. But who said that this is a source?
Yes.
The arrow is there, but that's fine. But who cares? Really, without the arrow, who said that this is a source?
Because RS من R source.
R source.
Forget about S and delete the RS and R. You put R1, R2.
VSS.
What's that? Delete VSS. You are kicking doing. I mean, give me a break here. Don't use the letters. خلاص. Letters are out. Huh? Okay, without that, how do you know that this is the source? The what? VD. Huh?
Because VD is on
But who told you this is VD? Huh? I told you. Repeat. That's what I'm saying. You are keeping the same. Huh?
There's no direction.
That's good. That's number one. That's number one. Yeah. But let's say I delete that. Yes. Let's keep going.
هذا الدكتور الحين ريزستر وش اللي بقى خلاص.
وحد الله. Look here. The voltage here is higher than here. And we said the drain is always higher than the source in an NMOS. See?
I thought you removed the whole voltage.
Yeah, I mean, you have to see everything. You have to look at the voltage, the current, the arrow, everything, you know. And so that next time, you don't make mistakes. Huh? And if you somebody playing around with circuit, what's this? You're joking. Right, good. So let's see. So design the circuit of this. So it's a design question. Okay, it's not analysis question. It's a design question. So we'll see what means analysis question and design question. Okay, we need to design the circuit. Determined by the value of RD, RS. So, what's this? That's what we need to know basically, because we need to design this using this and this. This is given to us. Let's see what we are given. The transistor operates at ID, so it's giving ID. It's giving VD, the VD here, this voltage. So this is given. This is given. What else? The NMOS transistor has VT, so VT is given. Good. Mu NCox is what? K or K prime?
Can. Because K prime multiplied by W over L.
No, this is K prime.
What is right? The rest are enjoying it. K prime, yeah. Oh, what? K prime, that's right. So K prime, that's why. Why? Because we don't have omega over L, because we use the equation K, not K prime. معناه ندخل K prime. صح ولا لا؟ Very easy to know. Alright, so we have K prime, we have L, we have W, and he said that neglect the channel length modulation effect. That means, well, so that is what was it? So we don't have the channel modulation parameter. So that's the question. Find me R and RS. This is a design, because once I do, I can determine ID. I can make ID if this is the. So basically, somebody, a customer, come to me. I need ID for this transistor. Is equal to this, and this is the transistor data sheet. Now find me RD, RS, please. It's a design because I have to plug this in. So how to solve this? So what do you think? Without looking at the textbook. Yeah, Mohammed Darwish.
VDD minus VD.
Nice try. Yes, Mahmoud. Yeah.
VDD minus VD over RD equal ID.
So the first, very good. So the RD is very simple. Yes or no? Because we know this voltage, we know this. So this divided by this. This minus this divided by that, we get RD.
Yes.
This we call it, what's that? This is, we call it straightforward solution. Yes or no? So, let's see. So now, RD becomes, check. Now RS. How to find RS? Who knows?
We have
Professor, ID that's in the VDD is different than ID in the RS, right?
Oh, easy. Who can answer this question?
Is it different?
What did you say?
ID and RD is it different than ID and RS?
Yeah.
Yeah, okay. So
They say it's different, huh?
Different names.
different names.
No, it is value. That's why the question.
Yeah, I'm talking about the value.
Values.
Yeah, they should be.
They should be different. Okay. Who doesn't agree with this? Think about it. Tell me.
No, it should be the same.
غير.
We have no modulation.
Huh?
We have no modulation.
It doesn't matter. It's not related to modulation.
You say VS is 0. Here we have VD.
No. We didn't say that. It's not related to that.
After finger.
If they are equal, why they are equal? That's the question. You said that they are equal or different?
What?
They are different or equal? Confused. Absolutely confused.
I don't think they're different.
They're different?
Yeah.
Okay, good. So who agree with Bilal?
I said it, so I agree with it.
You agree with him? Okay. Who else? يلا كلكم شجعان. مين اللي معاه واللي مين اللي ضده؟ أيوة. Who agrees with Bilal? They are different. ID here is different from ID here.
Not they are same.
لازم تغير.
Wait. I'm asking. They are the same or they are equal? Who said the same? Raise your hand. Who say different? لا في النص ما بيحزنون. انت خلاص different already. سراج الدين لا مع هذا ولا مع هذا. لازم تختار opinion. وانت الاخ الطيب هناك you are hiding. Alright, who said they are equal? We said the argument of this guy. He said that they are the same. So I'm asking this guy. Okay, why they are the same? ترى فاكرينك the same, yes or no? صح, explain.
I think the current does not divide. Right, same.
Exactly. Very simple actually, analogy. Where the current comes from here, where does it go? Does it go here, here? No. It's the only way it goes there. Is there any other way? It's KCL, KDL. It's KCL, huh? That's it. What's in goes out.
So, doctor, don't we say about the source and the drain, they're different?
Voltage, who cares?
But here we're doing like a voltage.
I don't care about that. Voltage, current is current. That's it. They are related through Ohm's law in the resistor. That's it. That's all what I know. But here I'm talking here about this current going through. I don't care about the really voltage. I care about KCL. In, out. That's it. What goes in comes out. What do you mean? Then in this guy, either this guy is generating current, so we have a machine that generates current, which is like a battery, which is not the case. This is not a battery now. Or this guy is gonna swallow currents more, and then at some point it has to explode or something, yes or no? So it's not neither this nor that, yes or no? So what comes into this device goes out. Simple. Very good observation. Simple. Life is simple. Energy. Did you get that? Good. So the current here is the same here. Make no mistake. So this is then what's next? How to find RS?
We get the V overdrive.
V overdrive. Okay, let's see. V overdrive is equal to what?
VT.
What's that? Forget that completely, yeah?
Minus VT, something minus VT.
Excellent.
VGS.
VGS minus VT.
Yeah, this is a proof that you are not revising at all.
Of course.
We haven't.
You are waiting for the exam. If not in the exam, it's out of the mind.
We have another.
No, but revision is regardless. I told you have to revise every day. When you study something, revise. That's all. This is a proof, guys, that the class is not following my recommendations. Proof, crystal clear. No one is revising. Alhamdulillah. 1-0. So V overdrive is VGS minus VT. Now VGS how much?
We need to
Calculate.
find it.
What do you mean from the circuit? From the circuit. VGS is equal to what? From the circuit. What is VGS in this circuit? VGS, how you calculate VGS?
V overdrive plus VT.
There you go. You're killing me now. Okay, I will solve it. I'm sure. I'm not counting on you guys. Khalas. You broke my hope now. VGS, what's VG? VG is 0.
So minus VS.
Khalas, that's it. You just say it. You didn't say it. Until I told you VG minus VS. Good morning. So V overdrive now is minus VS minus VT. So this is number 1. I'm not going to solve everything myself. You have to do it yourself. Okay? I will just give you the way, the methodology. That's the most important one. Very good. So the overdrive now depends on VS and VT. VT we know it. So V overdrive depends on VS, and VS depends on what? On RS. Yes or no? This is the other equation. I know this. So Vs is equal to what? Is equal to this voltage plus this drop of voltage. Yes or no? صح ولا لا؟ Vs, this voltage, Vs. This is the source, yes or no? So this voltage is equal to this voltage, and because this is referred to the ground, yes or no? It is going to be this voltage plus the voltage from here up through the resistor, yes or no? So it's going to be equal to what? To minus 2.5 volts plus Rs ID. And I know ID, yes or no?
Minus ID or ID?
What do you mean?
ID.
ID is going this way. So the voltage up, the voltage, the ID go from high to low. KCL, KVL, you even lost KCL, KVL. See, exams, they bomb basically your memory. They blow your memory away. KCL, KVL. Okay, great. So we have this. So that's good. So now we make the relationship between V over I and RS. We make it. From overdrive, we got Vs, and from Vs, we got the relation with Is. So if I put all together, I can get the relation between what? Between the overdrive and Rs. Make sense? Good. Playing games here, really. Engineering is fun.
So we have ID equal.
Now we are talking to ID. Now we use the ID equation. Now ID is equal to what? Half.
Okay.
And again, we don't have, it says that. Does it say something?
Not.
Really, seriously speaking, he has to tell us some more information.
It's saturation.
He is actually in saturation.
But we don't.
Automatically, why? Because he said, assume that is not. So that means he knows what he's doing. He's basically giving me a hint that is in saturation.
But maybe it's.
But there is no lambda in private. That's it. So he plays against me, I play against him. صح ولا لا? You understand?
Instead of giving VS with VT, I don't know. Can't you just do like RD is VDD minus VD? I mean ID is VDD minus VD over RD. Because we have VDD, we have VD.
But we found RD that's already.
Oh, okay, then what are we finding now?
RS.
Did you play copy to
We
this?
said they're equal.
No.
The currents are equal.
Oh, not the resistance.
Of course.
Okay.
You were absolutely out of here. No, we were talking that this is equal to this.
Oh,
It's
yeah.
equal. Of course.
Not the resistance.
So what we were talking about?
That's why I'm wondering.
Bilal, coffee on me. Okay, that's it. Okay, got it. So it's now in saturation. So half Kn, now V over drive square, yes or no? ID we have it or no? ID we have it. Bingo. We have it, ID is given. Yes or no? 0.4 milliamp.
No,
The end of the week and the break is next week, so I don't blame you. Okay? Alright, Kn we have it. Just we have this multiplied by W over L. That's it. So this is also given. Now the overdrive, now we establish the equation between the overdrive and RS. So, and V overdrive is equal to what? Let's do it here. So V overdrive is nothing but minus, here we have minus Vs. Minus of this. So it will be 2.5 minus RS ID. Yes or no? That's right. Yes or no?
Minus VT.
Minus VT. That's what we get from these two equations. Excellent. So we have here this squared. So we have ID squared on this side. Yes or no? That's the only thing. No. ID we know ID. Sorry.
Yeah.
We have RS squared here. When we choose here, put it here. What we end up with some stuff, including RS squared, yes or no? On one side, ID is given, everything is given. So it's the second order equation with a known RS. Makes sense? So the solution of this, I'll not give it to you. You have to go and read and solve it yourself. So here we will have RS1 and RS2. Yes or no? This is the solution. One of them has to make sense. The other one will not have to make sense. How?
Negative. I must have a negative.
That's a possibility.
No, that's
That's a possibility. Resistance cannot be negative, although there is a negative resistance.
Yeah, but
In this case, it should not be negative. Okay? And what else? So, could be that. Could be that if I put
it's
RS here, whatever I put, I have to make sure that first of all, I have the overdrive is positive when I replace that, because overdrive I can calculate this or no. I have to calculate overdrive, because overdrive depends on RS, yes or no. So I have to bring RS here and calculate the overdrive. And I have to make sure that VDS is bigger than overdrive, for example, to make sure that I am in saturation. So one of these assumptions is broken by one of these values of RS1 or RS2.
But I can avoid this by finding the value of V overdrive.
But V overdrive depends on RS.
Yeah,
So
yeah.
for each RS, I have V overdrive.
Yeah,
So I have to check V overdrive.
yeah, one of them will be absolutely.
Who knows? Maybe V overdrive, they are very close to values. So you have to make sure that the transistor is in saturation, and you know the condition that VDS, which is this minus this, is above V overdrive. So, well, and then it has to be consistent. It cannot contradict. Fun, that's the way. We go slowly but surely. But the end of the term, not the end of the term, end of the exams, KCL is gone, things like that. So stuff is really out of touch here. Anyways, move on this. So quickly, let's keep going. Please solve it at home, okay? I just give you the rules outline, the way how to do it. Okay. Now we come to the real stuff, not the real stuff, the end of the stuff, which is basically to use now the amplifier. Now, so far we did build the model for a MOSFET, complete. Now we need to use it as an amplifier. Excellent. So in that case, as an amplifier, we have to make sure that my MOSFET is working, like for this example, we have to make sure that my MOSFET is in saturation. And once I know that, I can put a small signal, and that's why we call it a small signal model, or modeling, or amplification of the using the MOSFET. So we put on top of the DC value, which is biasing this transistor to operate at a certain point. We'll talk about biasing later on. And on top of this, we put an AC signal here, and we collect it at the output. For this typical circuit, the output is going to be in the drain, because the source, we don't have the output there. It's actually ground in this case. So, changing the AC signal, which is going to be small, we'll talk about that, and we get here the AC signal here. And that's how the amplification. Put the input, put the signal at the input, collect it at the output, wish for the best to have a good amplification. Alright. That's it basically. So this is basically a typical amplifier. Okay. We have to bias it. Biasing means I have to supply the DC voltages that make sure that my MOSFET is working at certain point. We call it operating point. We'll talk about that later. And that at that point, I can amplify a small AC signal. Okay. We'll go slowly. Yeah, don't worry. All right. Good. So in that case, coming back to this. So here, just to remind you that, again, remember that, instantaneous constant value parameter, things like that. This is what? This is the instantaneous voltage, yes or no? Which include what? A DC plus AC. Remember that?
Yes.
So now, the transistor now is subject to two things. A DC plus an AC. So VGS, I have to write it accordingly, yes or no? So that's the way. Where's VGS? Now, VGS, this is the instantaneous, is equal to DC plus AC. Yes or no? I have to use that in the equation of the current. Yes or no? So bingo. Put it here. VGS. Yes or no? That's VGS. So here we are neglecting lambda. So lambda is 0. Why? Because we want to see the effect of this small signal. We want to see the effect of this guy. That's the question. The VGS, the AC VGS. This is the DC VGS, this is the AC VGS. Because we have a battery and we have an AC there. So that AC belongs to VGS. Okay? Alright, any question? So far so good. Good, okay. Excellent. VGS, we just replace it by Oh, what's that? Oh, no. We just put this together, minus VT with the big VGS. And we have VGS alone. And then we spread this. We calculate it. So it has this VGS minus VT squared. And then plus VGS squared. And we have 2 times VGS minus VT times VGS, which is this one. That's it. So this is basically nothing but this square. That's it. Come down. Alright. Simplification. Then we spread the parameters, blah blah, and we have this. So, first things first, let's see, it's going there. Okay, good. So, that's basically the equation that we studied here, that we found here, is just repeated in here. That's it. We just put them together. Now, some analysis. This is nothing but the DC current, because there's no AC here. It's exactly the DC ID that we studied, yes or no? That we call it DC bias. Okay, good. This one is, there's really interesting stuff in here. I have some kind of constant here on one side times an AC. That's very good. That means I have here a relationship. I have a linear equation here that relates. Basically, this is what? This is a current. Of course, we call it what? We call it the AC current. AD. Small z. A small I, a small t. So this is basically the AC current that I will generate in the drain. Very good. Now the last term is a nonlinear line because VGS now it becomes squared. Not only that, I say VGS is small, so squared it becomes smaller. Yes or no? Well, really, thank you very much. I'm not interested. Because VGS is a small. We said VGS is small. We don't want really, if small, squared or amplified, like, take 0.1 and enjoy. That's what I used to when I was a kid. 0.1 times 12, and then I go to 0. Okay? So when you have small amount, you multiply it by itself or in parallel, it becomes even smaller. Okay? So I can neglect it. Okay? So I have two things in here. I have a DC current and I have an AC current with instantaneous current. Okay? That's it. See? Nice visualization. I love it. Thank you, Microsoft. Alright, good. Sometimes we don't like Bill Gates, but sometimes this company does a good job. Anyways, so now we have the DC current plus an AC current, and then this is basically is equal to the AC current, and this current is related to an AC voltage. Yeah, very good. A voltage creates a current, that means there's a resistance. That's very good. There's a resistance, or there's a new parameter here specific for the MOSFET. I'll tell you why we call it that way. It's actually here is the inverse of a resistance. Okay? It's the inverse of the resistance. In unit is actually on minus 1. Okay. By dividing ID by VGS, why we do that? Because VGS is what? Is the input.
Yes.
And the output is what? Is this AC? Like business. I have an input, then I have the output. So I need to compare the two. So by dividing the AC current here, which is this one, by the AC voltage, which is this guy, I will find a certain constant here, Kn VGS minus VT. We call it the MOSFET transconductance. Why transconductance? Because the voltage at the input creating current at the output. That's why the word trans. It transits from one side, from the input to the output. And conductance because the conductance is the inverse of the resistance. So transconductance. Enjoy. The last, very important parameter you will see later on why. So this is basically where we arrived. Very good. So drawing the curve of ID versus VGS that we saw last time, it starts at VT, and goes. It's exponential. It's a quadratic, yes or no? Because remember, here we are here. What's that?
Square.
Okay. Here we have to make sure that we are in desaturation. Because here, with that saturation means here we must have a condition that VDS is bigger than the overdrive. Okay? We have to make sure that. Because here the picture only relates ID with VGS. Okay? Good. So if VDS is above the overdrive, we have this relationship. What's this relationship? It's actually ID. I use the DC or instantaneous. We can use the instantaneous, that's fine. The total means is equal to half Kn over drive square, which is VGS, minus VT squared. Yes or no? Ignoring London, okay? So that's why it's quadratic. It's like quadratic means power 2. Okay, you got that? Very good. So that's the point. Okay, when I set a DC point, that means I set VGS here. Through my circuit, I make sure that VGS is equal to this. So that means I will have the current at this point, because this is the current. If I set this, I get this. Yes or no? So this is. Now, when I add a certain AC signal, that means I make VGS on top of this DC. I make it changing. This is what? This is the AC voltage that I put on top of the gate. Yes or no? When I do change here, the output ID is actually changing like that. And that's what amplification is. Exactly, yeah. This is the input. This x-axis is always the input. The y is output. See? It's as if we heard it for the first time. It makes sense, huh? Because it's always like that. Math, x is in, y is out. But nobody told you that y is out and x is in. X is the input. They put it in, you get the y. That's it. But now we see it in the electronic circuits. What's that? It's just AC. Here is the time, if you will. Here is my, if I change a little bit this voltage, that's how my output current will change. It's like a reflection, because it means that if it is here, where's the current? So I have to go up, it's going to be here. If it goes a little bit there, so the next value, so it will follow. Do you understand? Yeah. It will follow. It's like a mirror. Send the light from here, receive it from there. And now, got it? Good? Too much today, yeah? I'm killing you guys. You have to have a nice break, right? So that's the way, yeah? That's the way. That's exactly the way. So, and the cross conductance, just to finalize this slide, is nothing but the slope actually. So the slope, right at this point. At this point, what we call it? The bias point. Or the operating point. Or where my transistor is working or playing. That's what we call it. And the slope is there, is actually the derivative of the current versus VGS. If you derive this, you will find GM. Let's do that. Let's do that, right? Derive ID versus what? VGS. This is equal to what? The derive. 2 goes down with this, so by 5. So it will be, that's right, Kn is constant. So when we derive this, it will become 2. The derivation of inside VGS is actually 1, yes or no? And times this power 1, VGS, minus VT. Pure math. It's not KCL, KVL. Now primary almost. Yes or no? Good. So this is equal to what? Yeah. This by with this. It's going to be Kn, VGS, minus VT. And that's basically the definition of GM, which is nothing but exactly the previous value. Did you get that? That's a graphical way. This is analytical way. Math, beautiful math. What can we say? God bless math. Alright, good. So we got that. The voltage gain. Let's finish with this and that's it. We call it a day. How is that? Because we are on the same circuit. Let's do it. So now we basically did the transconductance, we found it. Now we need to find the voltage gain because we are presenting here voltage. I need to see the voltage outside. Good, excellent. So now the voltage here at this point is actually the whole voltage here. So it's nothing but VDS actually because 0 is 0. So the output is VDS. So VDS is equal to what? VDD minus the drop of voltage. Yes or no? Nothing fancy here. VDD, DRD. ID now is the DC plus the AC. Then here we have an AC. Yes or no? So now pertaining to current in the drain, we'll have the DC plus AC. That's it. So what else we do? So we bring together things. This is DC, DC, put that together. and that's basically the DC component of VDS. صح ولا لا؟ لأن VDS here is equal to what? Is equal to the DC plus the ACDS. صح ولا لا؟ AC voltage. Yes or no? Make sense? Good. So this is the DC, and this is going to be what? The AC signal. And the AC signal is equal to what? Is minus RD, because it's plus this, huh? Plus this, no mistake. So minus RD is actually VDS. Simple. It's a game, I've told you, it's a game. VDS is continuous, is DC plus AC. Excellent. Enjoy. So now, this is what we found just now. Excellent. And ID, I know it has a relationship with the VGS, the AC, yes or no? Through GM, yes or no? That we found last time. So minus RDGM, VGS is going to be ID, the AC signal here. Oh, thank you very much. So I have a relationship between what? Between a voltage and the voltage. This is what? This is the input. And this is what? Output. And the gain is what? Output divided by input. Output by input is minus GM RD. And that's the gain. Negative gain. Negative gain in signal, that means the signal will be upside down. If it is up, the output will be down, or if it is positive, the output will be negative, and vice versa. That means they have a phase of 180 between them. Yes or no? Excellent. And in terms of module, is magnitude is GM RD, and that's the amplification factor. That's it. So let's see. That's it. So as you can see here, so we have VDS, VGS, that's the input. It has a DC value, and there's an AC on top of that changing, which leads to a VDS value, which is the DC value, plus on top of that the AC. And the relationship between the two, the peak to peak or peak value to peak value is the same. If you compare the whole thing, you have to use the same. If you use just the peak value, you can choose the peak value, same. You have to have the same comparison. So, if this is voltage, this guy has to be multiplied by GLRT, the gain. That's it. And this is going up, it will go down here, opposite of each other, yes or no? And that's it. So that's it. So we will take, inshallah, next time from this. So we end up by 5.53. Inshallah, next time, inshallah, we'll continue from that onward. Thank you very much. Have a good day. Thank you very much.